Okay there, hello everybody. Today we are looking at the higher P8 and 9 questions, all about forces and motion. So we're starting off with a question about an electric wheelchair which moves at a constant speed of 2.4 meters a second for 4.5 seconds. And we need to calculate the distance moved by the wheelchair. Now we are given the equation here, which is quite nice. Not always going to be given the equation. Some of them you are expected to remember. So we need to use distance equals speed times time. Now looking at the question, we've got our speed or velocity here as being 2.4 meters per second, and we've got our time as being 4.5 seconds. So all I'm going to do is I'm going to take 2.4, multiply that by 4.5, and multiplying those two numbers together should give us a distance of 10.8 meters. So that is the answer to our first question. Moving on to question 1b, we are looking at a reason for the speed of the wheelchair to be decreasing. Okay, so if the wheelchair moves at a constant speed, as it says in the previous question up there, constant speed of 2.4 meters per second, then that means that it's got to be something in the surroundings changing that is changing or causing its speed to decrease. So not necessarily going to be any of these last two. Okay, it's either going to be the first or the second. Now, if the speed is decreasing, then that means that it has to be starting to go uphill. So uphill would make its speed decrease. If it was increasing, then it would be downhill. So it's starting going uphill is the answer that we're after there. Next, moving on to the third part of the question, part C. A student measured how the distance travelled by the wheelchair changed over time. Figure 2 shows a sketch graph of the results. So we've got section A, which is this first straight line here. I'm just going to put some points on this so I can tell myself where the changes are. Then got point B, then got point C, and I've then got, sections B, C, and then section D. Question C says, in which section of the graph, A, B, C, or D, did the wheelchair travel fastest? Give the reason for your answer. Okay, so we're looking at a distance time graph. Now, a key thing with distance time graphs, a key feature of them, is their gradients. Now, the way you'd find the gradient of any line on any graph is by looking at the change in y over the change in x. Okay, now we've got a distance time graph here. So instead of y and x, we have, instead of y, distance. And instead of x, we've got time. So instead of me using y over x to find my gradient, I'm looking at distance over time to find my gradients. Now, it's not shown in the question above in the same format. If I just move my camera a bit, we've got distance equals speed times time, but this comes from the equation that you might have more often heard as speed equaling distance over time. So if speed is distance over time, and the gradient of our graph is also worked out by doing distance over time, then the gradient must be the speed of the object. Now I'm trying to find where the wheelchair is going at its highest speed, so where the gradient is highest. And higher gradients are steeper. So I'm looking for the highest speed, the highest gradient, and so the steepest line. And the steepest line is section D. So for my answer up here, for part C of this question, I'm going to write section D as my answer. I'm going to write because the gradient is the steepest. Now this is a 2-mark question, so I'd get 1 mark for the section and 1 mark for the explanation as well. But all I need to write is gradient is the steepest, or it is the steepest. Or you could say something along the lines, if you want it to be a bit more wordy, and say it travels the furthest distance in the shortest amount of time, because it goes, we go back to the graph down here, more distance is covered, it goes up vertically further in less horizontal distance along my graph. So more distance is covered in less time than compared to the rest of the sections, which also would mean it's going faster. Then moving on to part D, The student used a data logger with a distance sensor to record the data. Give 2 advantages of using a data logger rather than using a stop clock and a tape measure. Now, data loggers and distance sensors, because they don't have us using them, because it's an automatic electronic thing, it's going to be much quicker and better at recording data than us, much more accurately. You can take more measurements. It's no calculations needing to be done by us. It can essentially do everything for us. And so anything along those lines can be given. You could have said a whole host of things for this, but something along the lines of data logger more accurate would do for one. Data logger more accurate. And the other one that I would say is the more common answer I would see in this sort of question is less human error. Which means human reaction times is about 200 milliseconds. Every time you press the stopwatch, it adds on 200 milliseconds because of us reacting and that reaction time. You could have said, like I said earlier, you could have said the logger is automatic. That's another one you could have said. Or you could have also said something along the lines of logger takes more readings. They would also be acceptable answers. Okay, part E of this question on the not quite the penultimate part of question 1. Figure 3 shows a sketch graph of the velocity of the wheelchair changes as it accelerates to its top speed. Figure 3 shows a sketch graph of these changes. So here's our constant speed of 2.4. We then accelerate, here's our constant speed of 2.4, perhaps at some point here. We are accelerating and eventually reach our top speed here. The forward force on the wheelchair is constant as it accelerates on flat ground. Which force reduces the acceleration? Okay, we're talking about motion, so I've got 4 forces to pick from: magnetism, tension, or weight. Out of all these forces, there is only one that particularly links with motion, and that is air resistance. Anytime you have a moving object and it's in atmosphere or in water, then there's going to be air or water resistance acting on it. Most objects in a physics question sense will be moving in air or in water, so you're always going to have air or water resistance acting in those situations. The only time you wouldn't is when you're looking at, something in space. In a vacuum, no air resistance there. Okay? Right, turning over then to the last part of the question, question 1F. Explain the acceleration of the wheelchair at point E on figure 3. So I'm going to flip back and show you point E on figure 3. Point E is this point here. The line is very much flat. It has been for quite a while. So we have a velocity of about here. Our velocity is not changing. Okay, we have a constant speed at this point. So I'm just writing some notes right now on this for part F of this question. We have a constant speed at this point because the velocity is not changing. Time is passing by, but the velocity is not going up or down. So we have a constant speed. That's something I can use to describe it. And if I have a constant speed, well, how does that change my acceleration, and what forces might be involved here as well? That's what this question is asking us to talk about. So explain the acceleration. We're essentially linking this in with F equals ma, which is the equation that we use to represent Newton's second law, F equals ma. So explain the acceleration of the wheelchair at point E. We've got a constant speed, as we've just seen. I'm going to say velocity actually, because that's what it says on the graph. So constant velocity. And if we've got a constant velocity, we can't have any acceleration. Acceleration is when my velocity is changing. But if I've got a constant velocity, that means I have no acceleration. If I've got no acceleration, that means there's no force. But that's not quite true, me saying that. Not that there's no force, but there's no resultant force. So all I've done is I've added a little subscript R to there to say force resultant. Now that's a bit of terminology I might use in A level, but I'll use it here because it helps me get my point across. Okay, the resultant force is 0. There is still a forwards force acting on the wheelchair. There is still a backwards force acting on the wheelchair. If I were to draw a free body force diagram of this wheelchair, not a precise one because I'm using a pen and I'm not using a ruler, but something like that is what we would see. And the force here would be the same, F1 would be the same as F2 in this situation, which means there is no resultant force because F1 subtract F2 would equal 0. Okay, and that's the key thing I'm trying to get across here. F1 subtract F2 would equal 0. There is no force that is resultant. So constant velocity, so no acceleration, because, and that is happening because the resultant force is 0. Crikey, very long question. So, final part now, part G. The wheelchair starts from rest. It accelerates at a constant rate until it has a speed of 1.5 meters per second. The wheelchair travels a distance of 2 meters while it is accelerating. Calculate the acceleration of the wheelchair using the physics equation sheet. So, just bear with me 1 second whilst I grab my physics equation sheet, and then we can pick our correct equation off of that. Okay, so if I just pick up my camera and drop the data sheet down underneath. This is a data sheet for the combined science, physics. We have got a bunch of different equations on here. Now, there is only one of these equations that involves all the terms we are looking at. If I just try and drop the question sheet over the top for a second, we've got a speed of 1.5 meters a second being achieved at the end. So this is going to be what we'd call our final velocity, which we might use the symbol V for, but I'll write it down as well. Final velocity. We've got a distance of 2 meters, tells us here. We then need to calculate the acceleration on the wheelchair. Oh, one more point I've missed. It starts from rest. So if it starts from rest, then that would be what we call U, or the initial or start velocity. So I've got my initial velocity being U, my final velocity being V, I've got the distance being 2 meters, and I need to calculate the acceleration of the wheelchair. So what I'd be looking at doing here is I'd be looking at using the equation that has final velocity, initial velocity, and a distance in it. Now if I go back to my equation sheet, it's the very first one up here. It's got initial velocity, final velocity, acceleration, and distance. And we call it a SUVAT equation. If any of you go and study A-level physics, you will become much more familiar with SUVAT and or A-level maths. We call it SUVAT because we've got the 5 terms S, U, V, A, and T. S is distance, U is initial velocity, V is final velocity, A is acceleration, and T, which is not included in this particular SUVAT equation, is for time. Okay, so I'm going to write down this in symbol form just because I don't have the space to write it out in full. I've written the symbols next to each of the bits on the worksheet for what U, V, and S are on here, so I can then use that to help myself work this out. So let's get that equation written down on my question sheet. Okay, I've got the equation V squared minus U squared equals 2 times A times S. So 1.5 squared minus rest. Well, what's rest? Rest isn't given to me as a number. Rest means stationary, so it's going to be 0. So if I start writing this out, I'm going to have 1.5 meters per second squared minus 0 meters per second squared equals 2 times my acceleration. Now, this is what I'm trying to work out for my final answer. So that's what stays as a symbol, A. And then S, which is my symbol for distance or displacement, which in this case is 2.0. So there's my equation written out. If ever you get given a question that involves anything more than a calculation of 3 numbers and with multiplies divides, then I would recommend not trying to rearrange it from the start. I can try and rearrange this for A, and luckily it's quite easy to rearrange this for A. However, if I was trying to rearrange for V or U, it might become a little tougher. So any question that asks you to calculate with a more complicated equation than something like what we just used, speed equals distance over time, fully recommend following this method through instead, which instead of rearranging the equation at the start, all I would say is start trying to simplify, like you would in a maths lesson, okay, and work it through bit by bit. So what I'm going to do is I'm going to move my equation sheet to the side and grab my calculator, and I'm going to just start working out what some of these bits are. So the first bit that I'm going to work out is what 1.5 squared is. So 1.5 squared on my calculator gives me 9 over 4, which is 2.25. Minus 0 squared. Well, 0 squared is just 0. So that can disappear, and I'm just left with 2.25 on this side, being equal to 2 times 2.0, which is going to be 4, times A. Suddenly this is now a lot simpler to work with, just from having simplified it by one step. I need to get A by itself, so the way I'm going to get A by itself is divide 2.25 by 4. So I'm going to go ahead and rejig this now. I need to get rid of the 4 on this side, so I divide both sides by 4. The 4's would cancel out, and so I would be left with 2.25 divided by 4 equals A. And then I can just type that into my calculator. So 2.25 divided by 4 gives me an answer of 0.5625. Now, I would probably round that a little further. It does not ask me anywhere in the question to give my answer to a specific number of significant figures, but I would round it to the same number of significant figures. Unless you are told otherwise, I would... you can either write the full answer, or in my case, I'd just prefer to round it to the same number of significant figures I'm given here, which is 2 and 2. So I'm just going to call my answer 0.56 on my final answer line. And that is question 1. Okay, so moving on to question 2 then. This question is about forces, quantities, and vectors. Write down the equation that links gravitational field strength, mass, and weight. Okay, so that's an equation that links gravitational field strength, which would be the symbol G, mass, which would be the symbol W, and weight, M, and weight, which would be the symbol W. Okay, now this is very, very, very similar to F equals ma. Okay, it isn't F equals ma. It's essentially the same thing, but I'm being specific about what my acceleration is. It's the acceleration due to gravity. And I'm being specific about what my force is. It's weight. Okay, so this is essentially how weight causes objects to accelerate, and how your mass would change the weight of an object. So where that would be F, M, and A, this is W, M, and G. And so the equation for this is just weight equals mass times gravitational field strength. And you sometimes see this written as W equals mg. So, I'm told a small ball has a weight of 1.4 newtons, and gravitational field strength G is 9.8 newtons per kilogram. I've got to calculate the mass of the ball. So W equals mg, I need to rearrange that to try and get mass to be the subject of the equation. Now, with the equation before, which was quite complicated, I recommended not rearranging. With something like this, it's a bit easy to rearrange it from the start. I'm just trying to get mass by itself, so I'll divide through by G, and what my equation would look like is W over G equals M. Now, you could also use the triangles to solve something like this. Personally, I'm not a fan of equation triangles because it doesn't necessarily teach you a useful skill. If you can get the skill of rearranging this equation, you can use that to rearrange any equation. And you could, if you wanted to, rearrange the equation from question 1G. And it's quite a useful skill to have. Anyway, weight over gravitational field strength. So I'm going to take 1.4 newtons and divide that by 9.81 newtons per kilogram. Sorry, we're given 9.8 here, not 9.81. given an extra degree of precision there. So on my calculator, all I'm going to do is type 1.4 divided by 9.8, and that gives me an answer for the mass of this object as being 0.142857, and that whole section is recurring, indicated by the dots. Now, it doesn't say to give me an answer to a specific number of significant figures, so again, I'm just going to go to the same number as I'm given in the question, which is 2. So I'm going to write this down as 0.14 kilograms, or 140 grams. Okay, penultimate question of the page then. Question 2C. A white ball with mass 143 grams, thinking about that grams already and what I might need to do with it, is moving at a velocity of 7.9 meters per second. It collides with a red ball with mass 150 grams. The red ball is stationary before the collision. The white ball stops after the collision. Calculate the velocity of the red ball after the collision. Give your mass to 2 significant figures. Oh, sorry, your answer. So this time, I do need to be thinking about the number of significant figures I give. I'm given 3, and 2 here. So I would, maybe by my logic then, I would go for 2. And that is luckily what it asks me to do here, but always double checking the question. And luckily with the type of question that this is asking here, I don't actually need to convert my masses. Because they're both given to me in grams, I can just ignore the fact that they're in grams and just work it through to find my velocity. Okay? What we're looking at here is a change in momentum question. We're looking at the fact that momentum is conserved in any collision that we talk about at GCSE. So if momentum is conserved, the momentum I have at the start, which is the mass times the velocity of the white ball, is going to be equal to the momentum at the end, which is equal to the mass times the velocity of the red ball. Now, I'm not including the red ball in my momentum at the start because it's stationary, and my equation for momentum is that momentum is equal to the mass of the object multiplied by its velocity. So if it's not moving, the object doesn't have any momentum. So the red ball is stationary to begin with, so has no momentum. The white ball is stationary afterwards, so has no momentum either. So what I'd be looking at for the momentum at the start is just going to simply be 143 grams multiplied by the velocity, which is 7.9. So if I go ahead and grab my calculator, clear off my previous calculation, 143 multiplied by 7.9 gives me a momentum. Now, normally you'd have your units of momentum as being kilogram meters per second, but in this case, because I'm talking in grams, it's just going to be grams meters per second. And because I'm only finding a velocity here, I don't need to worry about conversions. You could convert it, but you'd convert both answers and it would just follow itself through and cancel out anyway, so not going to be needed here. So the momentum at the start is 143 times 7.9. That is 1,129.7. I'm not going to round yet. I only will save my rounding to 2 significant figures till the very end of the question. Otherwise, I'm going to change my calculation and ultimately change my final answer. Okay? So this is my momentum at the start. Grams, meters per second. Okay? Now I've got my momentum at the end. And what's going to happen here is I know the momentum because it's conserved. So the momentum I had at the start, if I just write mom at start is equal to the momentum at the end. So this number is the momentum at the end. Okay, I'm going to have mass, which I know is 150, times the velocity, which I don't know. So what my equation now is going to look like for mom end is going to be 150 multiplied by the velocity, which is v, I don't know it, multiplied by momentum at the start, which is the same as the momentum at the end. And now all I've got to do is divide through by 150 to find my final answer. So I'd be looking at 1,129.7 divided by 150 to give me my velocity. And like I said, there you go, because this is in grams and this is in grams per meters per second, or sorry, grams meters per second, does not matter about the fact that I haven't converted either of my numbers. And so that gives me an answer of 7.5313, and that 3 on the very end is recurring. Now, two significant figures. This is going to be worth a mark. This is why this is a 4-mark question, not a 3-mark question. Rounding this to two significant figures is going to give me an answer of 7.5 meters per second. Okay, forgetting about this, the 3 will not do anything to this 5, so it just becomes 7.5 as my final answer. Okay, moving on to the final question then, which is question 2D. The white ball is thrown high into the air. After it is released, the ball moves up and then back down in a vertical line. The free body force diagram in the figure below shows the forces on the ball at one point in its flight. The force arrows are drawn to scale. Explain what is happening to the ball at this point in its flight. So, free body force diagram. Try and simplify it. We have one object. We keep it simple as a circle or a square or something like that. It's drawn to scale, which means that this arrow being bigger than this arrow means that there are, or are they the same sizes? You know what? Why don't we get a ruler on this and double check? If it is drawn to scale, the sizes matter. I'm just going to move my camera slightly to the side so I can fit my ruler alongside. So, from tip to tail, this arrow is just less than a centimetre, about 0.9 centimetres. And if I go ahead and measure this arrow here, it's also 0.9 centimetres. So what that's telling me is if both arrows measure the same length, then the forces on each arrow are the same. Okay, now initially to me, when I was looking at this, it looked to me, and it still does look to me, like the top arrow is slightly bigger. However, you've just seen me measure. They are both 0.9 centimetres. So, a little note I'm going to write for myself to help me get my 4 marks is that the forces are equal. Now, thinking back to the previous question, question 1F, we had to explain the acceleration on that wheelchair at point E. And that was when it was at a constant velocity. So there was no acceleration because there was no resultant force. If here, these two forces are equal, but they are opposite in direction, then that means they're going to cancel out, and it means there isn't going to be a resultant force. So if there is no resultant force, that means the ball is either stationary or moving at a constant speed in one direction. Okay? It's been thrown into the air, so we know it has to be moving, which means that the ball is moving at a constant velocity. Okay? And that's one of the things that I'm going to need to talk about. Now, when we're talking about an object falling at a constant velocity, we call that the object's terminal velocity. So what I can say is 4 points, 4 marks. I know the ball is moving. I need to explain what is happening to the ball at this point in its flight. The ball is moving, and it's likely to be moving downwards. Okay, it's going to be moving downwards, and it's going to be at its terminal velocity. So the ball is moving down at its terminal velocity. You could write this as sentences. You could write the ball is moving down at its terminal velocity. I'm writing it into points just because it helps me when I'm writing my answers out, and it also is showing you what each of the 4 marks is going to be gained for. So the ball is moving down at its terminal velocity. Now I need to explain it. I've described what the ball is doing. I now need to explain. This is one of the sort of key words in this question. It's telling me what I need to do. I've described by saying what it's doing, but to explain, I need to say why it is doing that. Okay? And the reason why it is doing that is because the two forces are balanced. They have the same size or magnitude, but they are in opposite directions, so cancel out, so there is no resultant force, no acceleration. And I need to try and write that down to finish off. Okay? So the names of these two forces, if it's falling downwards, the upwards force would be air resistance. I'm just going to write air res for brevity. And the downwards force is going to be the weight of the white ball. Okay? So therefore, I'm going to say the air resistance and the weight are equal in size but opposite in direction. You could use the word magnitude instead of size if you'd like to. This means the resultant force is 0, and if the resultant force is 0, there is no acceleration, and so it's moving at a constant speed. Oh, I've just realised I didn't write the word velocity down here. Velocity. Sorry, that looks like a W there. Velocity. So this means no resultant force. So no acceleration. And there you go. 4 points for 4 marks. And that it concludes this worksheet.